Welcome to Statistics Beautiful. Today, alarming new YouTube video claims that birds aren't real. There's visitors from outer space. Hillary Clinton's emails caused California forest fires. They tell me, do your own research. Okay, internet, here I come. Now I get deluged by a flurry of pieces of evidence supporting the alarming doctrine. Each one pushes up my belief, my confidence in the possibility. Or does it? How do people become so convinced of things like this? Well, I don't, because I know the importance of conditional independence. After today, you will know too. There's what you know. We call that data. And there's something you want to know. We'll call that the unknown, the true state. The answer, aliens, yes or no? Are birds real or not? Where did all the feathers go? As for Hillary, oh no, feathers. Connect the dots. But we've got a bigger problem. Worry about a possible medical diagnosis, like the big C, cancer, or COVID. Got it or don't got it? That is the unknown that we really need to learn about. So we do a medical diagnostic test. Sure, we know how to use one test, one piece of evidence. That's Bayes' theorem. In episode 1, we learned how you start with some basic belief about the true state. A belief expressed as a probability. Probability P. Then you use new data to refine that initial belief. Get a new P. We applied Bayes' theorem to breast cancer screening with startling results. Refresh yourself at this link here if you want. The celebrated channel 3 Blue 1 Brown has an excellent video on the Bayesian method. But, just like my episode 1, it only deals with one piece of information. Today, a tougher problem. How to use not just one, but a whole series of pieces of information. What happens when another piece of information arrives about aliens, emails, birds, cancer, or COVID? How should we update our knowledge? Trickier. We have to learn about hidden ones and imposters. Dear old 3 Blue 1 Brown. Missing all the fun. Let's dive in to the key idea. Conditional independence. With the help of a pet turtle in the clutches of a child. But first, an alarming possibility. I start with a very low belief that the alarming possibility is true. I'm, after all, a reasonable human, huh? Then we get alarming new evidence, like a YouTube video or a medical report. From the depths of the 18th century, the Reverend Thomas Bayes speaks to us and tells us just what to do. Reverend Bayes tells me, start with that low initial belief, my credence, my personal probability, P. Convert it to odds, P over 1 minus P. Then just multiply the current odds, the initial prior odds, by the likelihood ratio. What the heck is that? The ratio of the two different explanations of how you could have gotten this report. If the alarming possibility is true, what's the chance I get this report? And if it's false, what's the chance I get this report? That's called the likelihood ratio. I promise we'll get back to the nutsy conspiracy theory stuff. Right now, we've got a patient to diagnose. Here is the setup in probabilities. The prior probability here is 1%. The odds is 1 to 99, and that's what we start with. This diagnosis seems like a long shot going in the door. The patient has a positive test result. If the patient is a plus D, if yes, that's the disease, then the probability is the sensitivity, 90%. But if the patient is a minus D, if no disease, then the probability is 1 minus the specificity, just 9%. So the likelihood ratio is 90 divided by 9. It is high. It's 10. So getting a positive test result is far more likely if the patient is sick, if the patient's a plus D. These are probabilities of a positive test given the truth, not probabilities of a truth given the positive test. Big difference. But now multiply the odds by the likelihood ratio and you've only boosted the odds from 1 to 99 up to 10 to 99. As a probability, that's 10 divided by 10 plus 99, which is about 9%. This app shows how the test data updates your belief, turns it into a predictive value, a posterior probability, a predictive probability. A link is in the dungeons. Episode 2 walks you through how to use it. Pretty easy. So getting a positive is far more likely if the person is sick. Well, that's good, but it's still just 9%. Oh boy, a 9% chance is hardly a diagnosis.
Let's say we just repeat the test.
Here comes more information, more data. What are we going to do with that? Suppose you get the same answer every time. R2 is positive, R3, R4 positive. Just multiply again by the same likelihood ratio. Right? Wrong.
No.
Let's pretend it's okay for now. Multiplying the odds by the same likelihood ratio again and again. Let's start with odds of 1 to 99. The first positive test, R1, brings the chance up to only 9%. The second one, R2, jacks it up to a half. 1 over 99 times 10 times 10 is just about 1. Odds of 1 to 1, probability of a half. Just keep multiplying by the next likelihood ratio. Easy, they all equal 10. R3 brings it to 91% and R4 to 99%. Zoom, zoom, zoom. Just look at all that evidence mounting up. It seems that plus D, the disease is present, is nearly a sure bet now. Or if it's about birds aren't real and we get 4 videos very convincing, then that's nearly a sure bet. Fun fact, logarithms turn multiplying into adding. So yes, we can keep multiplying the odds by the likelihood ratio, 10. Or even easier, we can keep adding the logarithm of 10, which is 1, to the logarithm of the log odds. It's the same thing. Each little up arrow has a length of 1. This table is made by another app, also with link in the dungeon. It's yours to play with. You can put in a whole sequence of report results and see what happens. We got to be careful, though. The first principle of Bayesian statistics, the key idea is always condition on all together. Like this. To condition on some facts means removing all possibilities that contradict the facts, then dividing by the probability of the facts. And so we multiply by the likelihood ratio. For the equation lover, here's all the gory details, if you want. In this case, just taking the first 2 reports, that becomes this. We've just replaced all the data by R1 and R2. If we're lucky, R1 and R2 are conditionally independent. Getting the right answer or wrong answer for R1 doesn't increase or decrease the chance of getting the right answer for R2. And that's good. It means R2 provides new information. Then you'd be able to ignore R1 in the second likelihood ratio. The truth helps predict R2, of course, but if conditional independence is true, then R1 doesn't add to predicting R2. Another way to say it is, conditional on the truth, R2 is independent of R1. A little equationizing shows that these 2 ideas are really the same. If 2 conditional independence claims are true, one for plus D and one for minus D, the numerator splits and the denominator splits. That justifies keeping on multiplying by 10 like we did before. You become more and more sure of yourself, which is not always a good thing. When you pretend there is conditional independence when there isn't, that's called Naïve Bayes. Worth a look in Wikipedia to see that sometimes being naive works pretty well for computer scientists. It turns out that Naïve Bayes can wreak havoc with both medical diagnosis and the viral spread of conspiracy theories. Let's find out why, shall we? Here's the same probability table we saw before. Same sensitivity, same specificity, same prior initial chance of disease. But something sneaky lurks underneath. The first test raises the chance from 1% to 9%, just as before. But the sequence of repeated tests doesn't keep jacking up the probability after the first test. None of the next reports deliver any new information. What is going on? I want my money back. Aha! The positive tests include genuinely false positives, because the patient has some other condition that the test is picking up when we don't want it to, a misdiagnosis, an imposter. In the lingo, the test is not specific for the disease that we are trying to detect. We'll call it ID. The letter I is for imposter. The person doesn't actually have the suspected disease. Bad for the person. They might get surgery that they don't need. What's just as bad, there can be genuine false negatives. Patients with the target disease that we do want to detect. They might have a variant of the disease. It's hidden disease, HD, sometimes called occult disease, but that sounds too much like being possessed by demons. In the lingo, the test is not sensitive to this variant. Bad for the patient. They might not get the surgery that they do need. Everybody with the disease we want to detect is plus D, either detectable true positives, DD, or hidden false negatives, HD. Everybody who we want to get a negative test is minus D, either no disease, true negatives, no D, or an imposter disease, false positives, high D. Now we can see why those tests 2, 3, and 4 were a waste of money, or blood, or whatever. Wow, if a patient gets a positive, the chance that report 2 is positive is 100%, regardless of whether diagnosable or imposter. And if negative, report 2 will be negative 100%, whether hidden or true not disease. Any data whose probability equals 1 is 100%, no matter what the truth is useless for discovering the truth. Looking at the bottom 2 rows of this table, the probabilities from the first table, showing probabilities for only plus D and minus D, have not changed a bit. So how do you get from the probabilities for the 4 subgroups to those for plus D and minus D, which is what we really care about? Here comes the second big principle of Bayesian statistics. We average over what we don't know, that we don't care about. In the lingo, we marginalize. So condition or subset on what you know, and average or marginalize over what you don't care about. That's it. Now you're a Bayesian. What's left? What we don't know but do care about. Example, suppose we care about the test's sensitivity, the probability of a positive given having the disease, plus D. We imagine, speculate that the next patient is a plus D person. So we condition on plus D and ask what is the chance of a positive test. So we average the sensitivities for the 2 groups that the plus Ds are made up out of. 100% for the detectables, 0% for the hiddens. The average is weighted by their probabilities. That's why it's the same plus D minus D marginal table as before. Successive false results share the same cause. Something about the particular patient, hidden or imposter, will give wrong answers, will explain many false positives and false negatives. If those subgroups explain all systematic repeatable errors, then conditional independence is true for each of the 4 subgroups of patients separately. In particular, for G equals the DD and HD, diagnosable and hidden, you get 0.9. You would have expected 0.9 times 0.9 or 0.81. Cool. But what about unsystematic errors? Random errors. We tinker with the probabilities to account for a 5% risk of a pure chance switcheroo screw-up. Within each group, the only errors are unsystematic random errors. Conditional independence indeed reigns supreme. The switcheroo, just pure chance. There's some screw-up somewhere. Some vials get mixed up. A reagent has gone bad. Equipment malfunctioned. Somebody writes down something wrong. It has nothing to do with that specific patient at all. So after conditioning on the explainers for the systematic errors, only random screw-ups occur. Ironically, for the hiddens and the imposters, these errors turn wrong answers into right answers. And now this is what the data say. Too bad we don't know who's who. However, here's the good news. As time passes, following up on what happens to the patients, we may learn the truth, which of the patients really had the disease and which didn't. So we learn which of the test results had been false. Actually, it could be that as time passes, a hidden disease becomes detectable. That's why every few years we repeat some cancer screening tests. And in a couple of days, we might take another COVID test. Time passes. Repeated screening, as the time elapses, is an important case, but we'll set that aside for now. Sometimes we can do biomedical research later and learn that these subgroups exist and find biomarkers for them. Now for the moment you've been waiting for. We return to those alarming conspiracy theories and algorithms. Let's choose birds aren't real. The algorithm recommends a video that shows that birds are actually all just Hillary Clinton wearing feathers. Oops, fact check. They're actually CIA spy robots. That's silly, but kind of fun. So you watch the video. That would be report R1. The algorithm feeds you another one, another proof. That would be report R2. Your posterior probability that the theory is true goes up a little bit, and then another, and then another. And there it goes, one compelling video after another. All these independent pieces of evidence. But oh wait, are they independent really? Or are they the equivalent of running your medical test report through the photocopier a bunch of times? Let's get serious about assessing a medical diagnosis being connected with assessing a conspiracy theory. One theory equals one patient. For conspiracy theories, what are the four categories? A plus D is a true theory. DD means the theory is detectable, that the evidence for it comes your way. HD means the evidence is hidden. Who's hiding the evidence? A conspiracy theory in its own right. Minus D, of course, means the theory is false. But what is an imposter? Something alarming is going on that is not our theory of interest, but generates misleading or misinterpreted or just plain false evidence that supports our theory. Could be a disinformation operation or a spoof. A perfect example is
Birds aren't real.
It turns out that the mountain of evidence for birds aren't real is not independent evidence after all. It originated with one founder, one prankster, Peter McIndoe. He's not a profiteer like so many conspiracy theory purveyors. Oh, there goes another one now. Instead, McIndoe had something to discover and teach. His TED Talk is worthwhile. So friends, be tolerant to our neighbors in media bubbles. They don't know about
Conditional independence.
Maybe send them this video. Ground News does not sponsor this video, neither does Snopes the fact-checker site, but I recommend them if you care about truth and don't want to fall victim to confirmation bias. Fodder for future videos related to conditional independence include Simpson's paradox, causal chains and colliders, Markov chains, hidden Markov chains for detecting genes, the wildly popular Monte Carlo Markov chain, and of course, turtles. Now we skate off with a little Professor Beautiful tuba music.